Alright, for this last video in sections 12.5 and 12.6, we're going to look at problem number 11 on the worksheet. It says, find the intersection of the helical path described by the vector function h of t, whose components are cosine t, sine t, and t, with the following surfaces. Okay, so first recall that we described this curve back in problem number 1, part C on the worksheet. This is a circular helix. Okay, so recall that if you project this helix onto the xy plane, you just get the unit circle, right? And you can see that by just looking at the I and the j components, right? This is a parameterization of the unit circle. And then the z coordinate, that's equal to t, that's an increasing function of t. So that's what's giving rise to this spiraling effect here. Okay, so another thing that we had pointed out back in problem 1, part C, is that since x squared plus y squared is equal to 1 from the Pythagorean identity, our helix lies on the circular cylinder, right, whose equation is x squared plus y squared is equal to 1. Okay, so with all that in mind, let's go ahead now and turn to part A. It says, find the intersection of the helical path with the xy plane. Okay, so looking just at this picture alone, we can see that our helix will intersect the xy plane at this one point along the positive x-axis. So what are the coordinates of that point? Well, if we're in the xy plane, the z-coordinate is 0. And for points on the curve, right, the z-coordinate is equal to t. So in other words, right, we'll intersect the xy plane when t is 0. So we find that the helix intersects the xy plane at the point whose coordinates are 1, 0, 0. Cool. Now for part B, it's similar question, but now we're looking at the intersection with the xz plane. So again, if we look at this picture here, think about how many points of intersection there are going to be. Well, there's actually going to be an infinite number, okay, in this case. So what are they? Well, if we're in the xz plane, we now want to set y equal to 0. And for points on the curve, the y coordinate is sine of t. So when is the sine of t 0? Well, it'll be 0 when t is an integer multiple of pi. Okay, so I can find the corresponding points of intersection by plugging in k pi in for t. Now the cosine of k pi, that's going to give you either a 1 or a negative 1, depending on whether the integer k is even or odd. It'll be positive 1 if k is even. It'll be negative 1 if k is odd. Now the sine of k pi, well, that's 0, which makes perfect sense. That's how we got k pi in the first place, right? We're looking at points in the xz plane. So the y coordinate is 0 at all those points. And then the z coordinates, well, that's just given by k pi, right? And here's a couple of them here for various values of k. So when k is negative 2, we're at the point 1, 0, negative 2 pi. That's down here, where we're intersecting the xz plane. And then when k is negative 1, we jump over here to negative 1, 0, negative pi. Then when k is 0, we're at the point 1, 0, 0, which notice was also the point where the helix intersected the xy plane. When k is 1, we get negative 1, 0 pi, then 1, 0, 2 pi, so on and so forth. Yep, so we're going to get an infinite number of points of intersection in this case. Cool, all right, so now that leaves part C. And here we're looking for the intersection of our helix with this sphere centered at the origin of radius root 5. Now it's hard to tell, right, how many points of intersection there will be from this picture alone, right? But as you might suspect, there ought to be 2, but it, maybe again is unclear from this picture alone. You have to take into account the radius of the sphere, and in any event, let's go ahead and actually compute what these points are. So here's the idea. Okay, I'm going to set x equal to cosine t, y equal to sine t, and z equal to t. Right? Those are just the coordinates, right, for the corresponding points on the curve. I'm going to set those, right, in for the sphere equation. And so that's going to give me what? Cos squared t plus sine squared t plus t squared. Right, that's the left-hand side of the sphere equation. Right now, in terms of the coordinate functions for our helix. All right, so now let's solve for t. Well, cos squared plus sine squared, that's 1. And so if I subtract the 1 from both sides, I get that t squared is 4. And so t then itself is either positive 2 or negative 2. Okay, so this gives rise to 2 points of intersection. So notice if you plug in negative 2, you get cos negative 2 and sine negative 2. And then using the even and odd properties of cosine and sine, right, those are just cos 2 and negative sine 2. So your 2 points of intersection are cos 2 sine 2, 2, and cos 2 negative sine 2, negative 2. So it's interesting to note here that the x-coordinates are the same, and the y and the z-coordinates are opposites of one another. Okay, so we're going to get, right, 2 points of intersection. They're going to lie in the plane where x is cosine 2, and that's going to give us a point. The first point there is going to be a point in the first octant there where y and z are positive, and then you're going to have this other point here where the y and the z coordinates are negatives. All right, cool. Well, that's going to do it for this video and for these sections. Thank you so much.